Okay, hi everyone, let's get started. Sorry about the wait. Okay, I'm gonna share my screen. All right, can everyone see this? Can I get some confirmations maybe in the chat? Right. So welcome to the midterm review. Hopefully this will be helpful for you guys, and we'll be reviewing some of the content for the first hour, and then for the second hour, we'll be splitting into breakout rooms and then kind of going over the additional practice problems that you guys are given to give you guys some practice for the midterm. So just some basic administrative stuff. So the midterm is this upcoming Wednesday, and there's 3 starting times. So 9 a.m., 3 p.m., or 9 p.m., all Eastern time. So you can choose the one that works best for you. And this will be open notes and open internet. So you can use anything from a Canvas or your own written notes, and you can also Google things. But we ask that you do not collaborate during the exam. So don't post anything like asking for help on like an online form or anything. And obviously this goes with the honor code policy, and in the end it only hurts you if you I guess like reveal exam questions to your peers, because it'll only hurt the curve. And as a reminder, there's no lab from March 1st to 12th, so no lab this week as well. So just some general exam review. Usually our exam has about 27 multiple choice questions, and then the last 2 questions are free response questions where you'll be coding something. And question 25 is about iterators, so definitely recommend that you review like more in-depth iterators. We'll also have a section in this shortly where we talk about the constructors and different functions you can use and stuff like that. Things that you can review include lecture and lab slides. I think that's like the bulk of the content for this class. Obviously, like rewatching recordings if maybe some of the content you're not as sure on. I think Canvas quizzes are a good way to practice for multiple choice questions, especially the ones that are like more content focused. And then knowing the project algorithms, I think would be helpful because the projects are really designed for you to like really understand the algorithms that are being taught in this class. Another really useful resource is the class notes that were written by a former IA, Andrew Zhao. So you can find these on the Piazza post, 39. You guys want to check that out as well. Definitely not like required for you to read that or go through it, but I do think it is very helpful. It's a very in-depth explanation of the topics if you want to have further reading. So any questions on that? Okay. And also, yeah, you guys can pop any questions in the chat if you have any, and we'll have some people answer as we go. So we'll get right into the content review. So we'll start with complexity and recurrence. So we have these 3 types of asymptotic complexity that we look at. So we have big O, which is an upper bound, which is generally the worst case complexity. So it means that it grows at most as quickly as G. And then big omega is a lower bound, which would be the best case complexity. And then big theta is a tight bound, which is kind of our best estimate of how this function is growing. So just a general overview of like slowest growing to fastest growing. We have our constant time, which would be like O of 1, our linear time, which would be n or something with a constant in front of it, polynomials like n squared and cubed, exponential, which is like 2 to the n, and then factorial. So this is just like a graphical view of these complexities as they're growing. So something that is kind of like confusing is the average case versus the amortized complexity. So we'll kind of look at the difference between these two. So average case complexity refers to the average cost of the function over all possible inputs. So average case is the case that you would most likely get if you were just looking at one specific case. So this is like independent of all of the other cases. Amortized complexity refers to the average cost of the function over multiple operations. So for this kind of complexity, you want to assume that the function is called many times, and then you want to calculate the average over time. So for example, we can think of our vector pushback is amortized O of one time, because over a long period of time, it will eventually average out to be O of one time. So again, average case is like an isolated incident. What's most likely to happen at this one point in time? And amortized means over a long period of time, what is the average of each operation? So as an example, suppose you work at an ice cream store and every day end customers arrive and they're each ordering a few ice creams. So we'll just assume that a few ice creams mean like constant, like a constant number of ice creams. So it would be something that you could easily count and wouldn't be growing like exponentially or anything. And then at the end of every day, a food critic arrives and orders the total number of ice creams ordered over the entire day before the food critic cubed. So basically, however many ice creams were ordered that day by all of the other customers, this food critic is going to order that number to the power of 3. So the operation is selling an ice cream to a customer. So that would be like one step in the operation. And then the resource is the number of ice creams sold. So we want to find what is the average case complexity of selling an ice cream, and then what is the amortized complexity of selling ice cream over an entire day. So again, like we saw earlier, the average customer is going to order a constant number of ice creams. So we would call this O of 1, just because we're only looking at an isolated customer, independent of all the customers, we're most likely to get this O of 1 complexity. But if we want to look at amortized complexity, then it would be a little bit more complicated, and we can look at it through this analysis. So again, amortized means the average over the whole day. And each customer we can think of as having O of 1 ice creams, and the total number of ice creams is all the customers plus the food critic. So we're going to have our O of 1 times all of the customers, that's n, and then going to cube that, and then we're going to add O of 1 times n, which is the number of customers. So let's see. Yeah, I think this is a little bit confusing, but this first part of the equation, O of 1 times n cubed, that's what the food critic is ordering. And then all the rest of the customers is this O of 1 times n. And we add those together and we get about O of n cubed. And then we have to count how many operations do we have. So over the whole day, we have n plus 1 operations, where n is all the other customers, and then this 1 is the food critic. And then we're going to divide O of n cubed divided by this n plus 1, and then we'll get about O of n squared as our amortized time complexity. And then this kind of chart shows how it looks throughout the day. So just some general tips for analyzing time complexity. The lower order terms can be ignored. So if we have this n squared plus n plus 1, we can just shorten it down to O of n squared. And then the highest order coefficient should be ignored. So if there's a 3 in front of this n squared, we can kind of ignore it when we do our final time complexity approximation. And then usually the complexity of a loop can be inferred from its bounds. So yeah, there are exceptions. So you want to read the entire loop. So, but if you have like a for loop that goes, say, from like 0 to n, and then you're just adding 1 on every loop, then the time complexity would be about O of n. So those are good indicators for the complexity. Okay, and then next we'll talk a little bit about Master's theorem and recurrence. So a recurrence relation is describing the overall runtime on a problem of size n in terms of the runtime on smaller inputs. So an example of this would be the Fibonacci sequence, which we see here. It's like f of n equals f of n minus 2 plus f of n minus 1. So this f of n is going to depend on the runtime on these smaller inputs of n minus 2 and n minus 1. So the equation for the runtime of a recursive program, so there's three steps for making a recurrence relation. So we're going to identify the complexity of each recursive call, and then we're going to identify how much the input shrinks on each call, and then identify how many recurrence calls are made per iteration. So this is kind of the general format right here. So we have T of n equals how many recursive calls are made times how much the input shrinks, and then add the complexity of each recursive call. So we have this example right here. This is factorial. So if we look on lines 2 and 3, if n is equal to 0, then we're going to return 1. So the general complexity of like one call of this recurrence function is just O of 1 because it's just an if statement, so it's constant time. And then when we make a recursive call, we're going to call a factorial n minus 1. So this would give us the recursive, or the order, the input is shrinking from n to n minus 1 on each call. And then we're going to have this 1 in front, this 1 times this recursive call, because this recursive call is only called once each time. And then when it's returned, we just multiply it by n, which is just an integer. So just as a review of the master theorem, so we want T of n to be a monotonically increasing function. So what that means is that this function has to be strictly increasing, like as it grows, and it's going to satisfy this format. So T of n is equal to a times T of n over b plus f of n, where a is greater than or equal to 1 and b is greater than or equal to 1. And then f of n satisfies some polynomial big theta. And then we can look at this to give us our time complexity. So as an example, if we have T of n is equal to 2 times T of n over 2 plus O of n, then we have A is 2, so this first coefficient. B is 2, so the denominator of this lower order, or this smaller, the shrinking input size. And then this O of n gives us exponent of 1, so C is equal to 1. So then if we look, we have A is equal to 2, and then B to the C is equal to 2. So that means A is equal to B to the C, and that gives us this second line right here for our complexity. This tells us that T of n is equal to O of n log n. And we see that recurrence happens a lot in the different algorithms that we learned in this class. So different searches like binary search or like merge sort. And we can kind of look at the complexities based off of the master theorem. I see someone has raised their hand.
Yeah, sorry. I just had a question. So we're in the chat right now, and we were wondering if it was possible if the slides could be posted now, so it was easier to follow along while taking notes.
Yeah, sure.
All right, thank you.
Yeah, I'll just post on my Canvas now.
Okay, perfect. Thanks.
Yeah,
Nigel.
thank you for putting it out.
All right. Let's see. Any other questions?
This is from a little bit ago, but we're trying to distinguish between average case and amortized. And for the example of pushback, amortized is O1. I was curious what the average case for the pushback example would be. Is it also O1?
Yeah, so for pushback, yeah, in this case, they would be the same.
Okay.
So yeah, if you're pushing back something into a vector, it's most likely going to be constant time, right?
Gotcha. Thanks.
Yep. Any other questions?
So on that note, like, I guess you could say like the average runtime of the pushback function itself is just like, yeah, O of 1, but like when you do the like when you have to reallocate or allocate more memory, that's when you use the, I guess, yeah, the amortized complexity itself, and it's best, worse than average case complexity is O of 1, I guess.
For pushback?
Yeah.
Yeah,
So is
so
it O of 1 for the amortized?
The best, average, and the amortized are all O of 1, right? Because best case, it's you're just adding 1 into the container. Average case, you're most likely to just be adding 1 into the container. And amortized, as it's in one of the labs, I don't remember which one, but you can see like over time, it's about like O of 1 for each operation. But the worst case would be that O of n, where you're reallocating and then copying everything into a new container.
Gotcha.
All right. Any other questions?
Do you mind possibly giving an example of when the amortized time would not be equal to the average time? If that makes sense.
Yeah. So if we go back to this example, I guess this is just an example where amortized is not equal to average. So in this example, we have each customer is ordering O of 1 ice creams. So the average case would be O of 1 because you're most likely to have a customer that's just ordering a constant number of ice creams. But the amortized complexity, because we have this food critic who says, however many ice creams are ordered today, I want to order that to the third power, or that number cubed. So if we're analyzing the amortized complexity, that would be, so all of the total number of ice creams ordered that day, which would be about n cubed, over the number of operations, so, or the number of like orders that we have that day is about like n or n plus 1. And that gives us an amortized complexity of O of n squared.
Got it. Thank you so much.
Yep. All right. Any other questions? You guys can also pop questions in the chat as we go as well. Okay. So when can you not use master theorem? So you can't use the master theorem if T of n is not monotonically increasing. So in this example, we have like T of n is equal to sine n. So it's both increasing and decreasing as n grows, so that we can't use master theorem for that. If f of n is not a polynomial, we can't use it. And if b can't be expressed as a constant. So one example that of when we can't use it is if T of n is equal to T of n minus 1 plus n, because this shrinking input size is like decreasing by 1 instead of dividing by some constant number. So in this case, we would be using the substitution method. So just as a review of the substitution method, we would write out T of n minus 1, T of n minus 2, for example. And then we would substitute T of n minus 1 and T of n minus 2 into T of n and look for a pattern. And then as we're expanding these recurrence relations out, then we'll look for a pattern. And then eventually we'll use a summation formula to give us a complexity for that. Yeah, so I don't have an example for that, but I believe maybe in the practice problems or somewhere, you guys can have more practice with that. I know in one of the labs, we also had like a pretty detailed explanation of an example for this as well. So any questions before I hand it off? Okay, I believe Sabrina.
Yep.
Going
okay.
next? Okay, perfect.
So now we're going to switch over to arrays and linked lists. Okay, so first of all, an important distinction between linked lists and vectors is the way we access things. So for sequential access, that means that we have to begin at the ends of the data structure and linearly move to the nth item. So if you want to access like the 8th item, for example, in a linked list, you can't just go directly to it, right? You have to like start from the beginning and like go one by one until you reach the 8th item. Random access is different in that you can directly access any point in constant time. So if you want to see the 8th item of a vector, you can just do vector bracket operator 8th, right? And that'll return something in constant time. Okay, so array-based container, a vector is an example of an array-based container. The capacity is the number of elements that the underlying array is capable of holding, and you can change this capacity using vector.reserve. And the size, on the other hand, is the number of elements that are actually contained within the underlying array. You can change that size using vector.resize, also using pushback, right? Pushback, as we were talking about before, achieves amortized constant time. However, when we reallocate it, we need to do this in like one by one for everything inside of our vector, so it ends up being a big O of n complexity. Again, a good analogy for capacity and size is the buckets. That's the analogy we used in one of the previous labs. So if you have like a bucket of capacity of like 1 gallon, it doesn't mean that you have like water in it yet. It just means that you can hold up to 1 gallon. And switching, like using vector.reserve would be like equivalent to switching out to a bigger bucket. And then the size would be like how much water you actually have in the bucket. So that's a good analogy if you're a little confused about the difference between capacity and size. Okay, so linked lists only support sequential access. They don't support random access, right? And it requires a memory overhead for the node data structure, so keeping all the next pointers and the head pointers. Linked lists can be singly linked or doubly linked. A singly linked list only contains a pointer to the next node, but a doubly linked list will also contain a pointer to the previous node. And some of the invariants are that our last node has to be pointing, the next pointer is a null pointer all the time. And that means that you reached the end of your linked list. And if the list is empty, then the root node pointer is a null pointer. So that means that you don't have anything in your linked list. Okay, so now for choosing between an array and a linked list, usually a vector is the most effective or efficient. And that is because it's very cache friendly. Everything is together in space, so you have like really quick access to it. We have like the amortized constant push, so that's also super useful. And if your data types are small enough, copying and moving is not going to be a very like significant portion of the time you spend using the vector. However, there are times when you would want to use a linked list. So for example, the code is dominated by splitting and merging of very large lists, and you have verified this, and it might be better to use the linked list, right? Because you can like modify it, modify like the node, the next pointers very easily. Also, if you have to insert or delete a lot from the middle of the list, with a vector, you would have to rearrange everything in the vector. You can't just like take one thing out, but with a linked list, you can just take something out and like kind of like go around it with your next pointers. Right, and if you have measured and profiles that a linked list is better, then definitely go for a linked list. Okay, now just some more differences between arrays and linked lists. For access, as we were talking about before, arrays have constant random access and sequential and constant time access as well. Linked lists, they have linear random access and constant sequential access. For inserting and appending into these data structures, you can insert in big O of n time to an array, but you can append in constant time to a vector. And for a linked list, you can insert in constant time if you have a location. So you have a pointer to a node, then you can like insert right after it. And if you're appending, you do have to take constant time or linear time, sorry, to like reach the end, unless you have a pointer to the tail pointer, so the end of your linked list. In that case, you can add a node right after it. So for bookkeeping, for an array, we usually keep a pointer to the beginning and the size of your array, or a pointer to the end of the space that you used, and also a max size or a pointer to the end of the allocated space. For linked lists, however, we have more things to keep track of. So we have a head pointer to the first node in your linked list. You can have a size, this is optional, and also a tail pointer. Again, this is optional. But for each node, you need to keep a pointer to the next node. And if you have a doubly linked list, then you also need to keep a pointer to your previous node. And this is a lot of overhead, so this can be wasteful if you have small data items, which is why we would prefer to use a vector usually. Right, so for memory, an array will waste memory if it's oversized. So if you have like a lot of space, but you're only using a little of it, you're wasting a lot of it for no reason. And it also wastes time if it's repeatedly undersized. Okay, but for a linked list, you allocate a memory as needed, and but you do require that memory for the pointers that we were talking about. Okay, so now we're going to walk through deleting a node. So let's say that you're giving a pointer to the node that you want to delete. Is it possible to delete this in constant time? So we have a doubly linked list. It's not that complicated, right? You can just get the pointer that you want to delete. You can get its previous node and make its next node like the next node. And same for the next node. You make its previous node the node's previous node. So you're just like stitching up the list around the pointer or around the node that you want to delete. But what if your list is singly linked, so you don't have access to that previous pointer? This becomes a little bit harder because you can't just directly stitch up the list like we did before, but it is still possible. I don't know if we have time for you guys to like actually think about it, so I'll just give you the solution, I guess. But basically what you can do is, given the pointer to the node that you want to delete, you can access the content of the next node and copy it over to the node that you're trying to delete. And once you've done that, so you have like, you overwrote the content of the node that you're deleting, you delete the next node because you already copied that information. And now you can just make your node's next pointer, the node that you deleted, their next pointer. So this does assume that you can copy or move like the data stored within the node. But yeah, so basically you just delete the next one instead of deleting the one that you actually got the pointer to. Do you guys have any questions? Yeah, this assumes that you know the address. So you're giving a pointer to the node that you want to delete. And it's all in constant time for both examples, because you're just accessing the next pointer, getting its data, and then deleting it. Oh, this is only for deleting a single node that you're giving a pointer to. That's why it's constant time.
So just deleting not, never mind, sorry.
Okay. All right, so some more questions in the chat. So if a question asks, what's the time complexity of deleting a node from a singly linked list? What should we say? Right, so now you know that we can use this algorithm. So it would be constant time. But you have to copy every node until you get to the end. So no, because, so say you're giving a pointer to node A. So you look into node B and you copy node B's content into node A, and then you make node A's next pointer node C, which you can access from node B, right? All in constant time. And then you delete node B because you copied everything into node A. So it's like you're deleting node A, but you deleted node B. So that's why it's constant time. Okay, so if you're deleting the last node, it would be the same because you're given a pointer to that node. And I guess there's like nothing to copy over, so you just delete it. Okay. How do you update previous elements next? So you don't need to, because you're not actually deleting the pointer that you get. You're deleting the next one. So if we were deleting pointer B, oh, if you delete last element. Can you explain what you mean?
I know what he means if you want me to say.
Oh, okay, sure, go ahead.
Yeah, I mean, he's saying, so this works if like you're deleting from the middle, but if you're given the pointer to the last element, what do you do? Because there's nothing you can like copy in. There's like, there's no next. Next is null pointer, so there's nothing you can copy in. That's what he's asking. And I'm pretty sure this just doesn't work for the last element. You can't delete the last element with this.
Yeah, I see what you mean. Yeah, I don't think you could do anything in that case. So good catch. Of an edge case. I guess it would be big O fan for the last element. All right, if that's all the questions, I think we can move on. Oh, okay. I guess it's still my turn. Sorry about that. So now for container types. Okay, so a container is a class, a data structure, an abstract data type, ADT, whose instances are collections of other objects. In other words, they store objects in an organized way that follows specific access rules.
Sabrina, I'm sorry to interrupt. I think Gabe is supposed to do container types.
Okay, yeah, I didn't think that I had to
don't
do
think
them,
he's-
but is
Yeah.
he here right
he-
now?
I don't. Let me check if he's here.
Yeah, I was like not sure because I didn't remember
Yeah.
having to do them, but no one was speaking, so I just kept going. It's fine. I can go through it, I guess.
Yeah, he's not here. Okay.
Okay, yeah, no problem. Okay, yeah. So types of containers. Okay, so a container supports add and remove operation. A searchable container would also have find operations. A sequential container allows iteration over elements in some order. So that would be like a vector or a linked list, as we were talking about. And ordered container is a sequential container that also maintains current order. And you can arbitrarily insert new elements anywhere. So a good like distinction between ordered and sorted would be like, for ordered, you don't necessarily are like increasing or decreasing or something like that. But the important part is that everything to your left will stay to your left, and everything to your right will stay to your right. That's like a good way to think of it. Then for a sorted container, is a sequential container with a predefined order, and you cannot just arbitrarily insert elements. Okay, so here are some of the interfaces for sorted and ordered containers. So add element, the interface add element for a sorted container will override the searchable container version, and the ordered inherits from the searchable container. Remove value, you inherit from sorted, you inherited from ordered, same for find value. They both support the operator, the bracket operator, and also withdrawing the iterator. I don't know, I guess this is just something you guys can keep in your cheat sheet. I guess there's no point in me reading it out loud for you guys if you want to like move on to the next slide. Okay, so some common container complexities here again. So some of the ones that we've been talking about with arrays and linked lists with random access and inserting after. And then, so for arrays, you have random access with using the bracket operators and constant time, and inserting after you can do it in linear time, as well as deleting. For a linked list is how we were talking about before. It goes in linear time, and insert after and delete is constant time. But for a sorted container, in an array, you can find something in log n time, and using the bracket operator, you can use that in constant time, as well as deleting will be linear time. Is someone raising their hand?
Yeah, I have a quick question. So, like for example, the array find, you say it's O of log n, right? Is that average case, right?
Yeah, I think this would be the average case complexity.
So you're saying the amortized like time complexity will be O of n, is that right? No, I mean I'm saying it.
With a bind, well, is it okay if I jump in?
Yeah, go ahead. I haven't reviewed like this part of the slide, so if you guys like want to like add in, please go ahead.
So when they're talking about find on a sorted array, they're just talking about using binary search. So I'm pretty sure worst, best, average are all log n. There's no amortized for binary search because there's pretty much an equal amount of work every single time. It could be a little bit better than that, I guess, but amortized analysis doesn't really make sense with a binary search. If you were to do amortized analysis, I think it would still be log n, but it doesn't really make sense in this type of case. So yeah, amortized analysis is pretty much only used in cases like pushback.
Okay. Sorry. Yeah, just to add to that, yeah, amortized complexity, I feel like is most useful when you have like different operations have different complexities. So like in pushback, some of them are like constant time, some of them are O of n. But for like this binary search, every time you don't know what the complexity is, but it will be about log n.
Do you still have a question, or are you still raising your hand from before? Okay, I think it was just from before. All right, so some more distinctions. Oh, do you want to go to the next slide, please? Okay, so a sorted container is an iterable or searchable container that maintains a strict value-based comparison order that determines that order in which elements are iterated over. So again, think of like a sorted, something that would be sorted, like you would always expect to find like the next greatest or the next least or whatever like your sorting like invariant is, you would expect that to be followed all around. So if two sorted containers contain the exact same elements, they would be identical. For an ordered container, the general container, it's a general container where each element deterministically maintains its position specified by the user, regardless of what elements are added after it or come before it. For every collection of n elements, there may be up to n factorial different ordered containers that hold them. So that just means that you like have all your elements within the container, but they're not following like a specific sorted order. It just means that they're like next to each other. Okay, so is a here are some questions that you guys can think about for a second. Is a priority queue iterable or searchable? And is a priority queue an ordered container? And you might think back to project 2 for these two examples. So a priority queue is not iterable or searchable, right? Because if you remember back from project 2, like you only really had access to that top element. And if you wanted to look at the next ones, you had to like remove that top element. And is a priority queue an ordered container? Also no, right? Because if you remember from project 2, you got like the greatest or the least or whatever element is the top, but all the other ones after it were not necessarily following that order. They were just coming after. So the only guarantee that you got was that the top one would be the item with the highest priority. Okay, so now going over stacks and queues. So stacks follow last in, first out order, and queues follow first in, first out. So stacks are like pancakes and queues are like you waiting in line for something. Okay, so for a stack and a queue, you can use a deck for both. And you can also use a vector or a list for a stack or just a list for a queue. That's how they're implemented in the STL, I guess. Okay, so going a little more in depth into a stack. So stack supports push, pop, top or front, size, and empty operators. So push will add a value to the top of the stack, and pop also removes the item at the top of the stack. Top or front will return the value at the top of the stack, and size and empty just determine like how many elements are in your stack or if the size is equal to 0. Okay, now queues. Queues support like the same type of operations. So push will also append a value to the back of the queue, but when you pop, it removes from the front of the queue. So that's like the main difference from a stack. Top will also return the value at the front of a queue, and size or empty are the same as for a stack. So decks. Decks are great because they support efficient access to both the front and the back. So you can use them as a stack or a queue, which is what we did in project 1. And another nice thing about them is you can also traverse using iterators, and it also supports random access. So it's like you have everything in one. It supports constant time push front, push back, pop back, front back operator, bracket operator. So here, yeah, I guess that's the end of that. A simple implementation of a W linked list. Wait, what is this example?
Sorry, I think this is from the lab slides. Yeah. There's just like
okay.
the problem with this is you can't have constant.
Oh, right. So if you were to
access
implement a
them.
deck with like a doubly linked list, you would have access to like the front and the back, but you wouldn't be able to use the bracket operator. Right. I see there's a lot of things in the chat. Did all the questions get answered, or are there any that you guys still need to ask? So you wouldn't be able to use the bracket operator on this doubly linked list. This goes back to what we were talking about before. Linked lists don't support like constant access. Like if you wanted to look at it, the blue node, for example, the only way to get to that blue node is to start from the red node or the purple node and like work your way to the blue node. All right, so I think that's it for containers. Sorry if that was a little rough, guys. I had not reviewed those slides, but yeah, hopefully that's good.
All right, everyone, we're gonna continue with sets and union find. So if you have any questions, just feel free to unmute or say them in the chat. I'll try and cross-reference the chat as I go. So without further ado, sets are, let's set things up. So sets are just a collection of distinct elements. These are some of the set operations that you might have touched on in 203. For time's sake, we'll just continue. Next slide. So for all those set operations, for sorted data, they take linear. And when we get into breakout rooms, you want to go over those linear time code, and I'd be happy to go over any of them, like union, set difference, any of those. But for unsorted data, it generally takes longer, sometimes being O of n squared times, with the exception of hashing, but that will be a concept that we'll be learning next semester. So what we discussed in lab 4 was union find, and this is an algorithm used for disjoint sets or sets that don't have shared elements. And what we considered was what was the which element is the ultimate representative of the disjoint set, meaning to find out how many disjoint sets there were, there'd only be one ultimate rep that would kind of title the different disjoint sets. And we'll talk about this more when we get to the example, but the two most important parts of union find is union, which joins X and Y, they join to be a part of the same disjoint set, and find, where it returns the representative and you identify which disjoint set X belongs to. So I came up with like a short analogy that will help explain union find a lot better on the next slide. So suppose you want to figure out and find if two people are part of the same universities. So on the left here, you can see it's Michigan University with Mark Schlissel at the very top, and then State University with State's president and a bunch of other people that goes to Michigan State. You can see Professor Darden here, and then me and Morelli, another IA, and then we're all connected to Mark Schlissel, the president. So whenever we say, oh, what university does X belong to, or find on X, what you would do is you would find the person. So let's say you want to find what university I belong to. And then you'd say, okay, who is my boss? Who is my ultimate representative? And my immediate boss is Professor Darden. And Professor Darden's boss is Mark Schlissel. And then Mark Schlissel's boss is himself, because he owns the university. So by that logic, I belong to the University of Michigan. So the next two slides show the graphic a little better, if you want to continue. So once again, we check the boss and then just walk up the tree to find who's the main representative. There we go. And then what if we wanted to combine these two universities? So as of now, we had like a Michigan tree that had a bunch of people that belonged to Michigan, and then a state tree that belonged to, or that had a lot of people that went to Michigan State. But what if for some reason state was like, you know what, Michigan's just too good. We need to up our standards. We want to just combine with Michigan. And Michigan was just, you can combine, but it's still the University of Michigan. What would happen in that scenario? If you go to the next slide, what you would do is just have state's president, I don't even know their name, sorry, president of Michigan State, but you'd have state's ultimate representative point to Mark Schlissel. So now all this entire disjoint set is now connected with Michigan's disjoint set, and now it's one giant disjoint set where Mark Schlissel is the ultimate representative. We can continue and then talk about path compression. So path compression is a more efficient implementation of the find function, in which instead of asking or following up the tree to say, oh, who's my representative? And I would have to say, Professor Darden, and then Professor Darden's representative might be Mark Schlissel. If that call got really large, that would take a lot of time. So instead of that, we would change my representative just directly to Mark Schlissel, and that would improve the runtime. And I'll show that in the next slide. This is the code that you would use for path compression. After you find the ultimate representative, you would set the people along like the chain directly to that ultimate representative. The next slide displays the graphic. So you can see that if this is the analogy of Michigan, and this is your boy, this is me, and I'm pointing to Professor Darden, who's pointing to someone else, who's pointing to Mark Schlissel. If I were to be called on find multiple times, it would just be wasted time for me to call and follow up the chain every time. So instead, we'll use path compression, which after one call, the arrows would just point directly to Mark Schlissel. Right here. Right here. Nice. And this improves the runtime. And we can go more into specifics on how to implement it and how the code works in the breakout room. But for now on time, that's just a brief overview and analogy of union find. Oh, also, because Michigan just took over state in this union find example, take a break from your studies and watch the Michigan State basketball game starting at 4:30. All right.
Okay, cool. I'll start my video. Well, first off, how's everyone doing so far?
Good, good.
Awesome, I'm doing okay as well. I'm just getting through it. I wanted to talk to you guys briefly about the STL and iterators. Yeah. So for the exam, there will be some written questions, and if you've done the practice exams, you've probably gotten a good idea of what they look like. But on one of those problems, you'll usually be able to utilize the STL to solve it. So having a general idea of what all of the functions and data structures there are in the STL is going to be really important, as well as knowing how to use iterators. So these are some that you might have seen in your projects. So we have vector spaces, which are dynamically resizing arrays, right? We have the deck, which you used in project 1 and potentially in project 2 for your parent PQ implementation. We also have stacks and queues, which are pretty nice. And the priority queue, which was really important in part A of project 2. So I would say that does deck support the bracket operator? Yes, it does. Yep. So I would say just be familiar with the data structures that that you used in the projects, and you should be all set for the midterm. So in terms of going over like some use cases, vectors are really compact in memory and they're very cache local. What cache local means is that all of the elements in a vector are going to be contiguous in memory, which means they're going to be like one after the other. So like if you looked at the memory addresses of each element in a vector, then all of those are going to be in order sequentially. So that allows for you to have good access patterns in general. The vector also allows for you to have an amortized push and pop back, as well as allowing random access since it's just an underlying array. Decks are somewhat compact in memory. You might want to review the previous lectures on how those work. They're a bit more complex when compared to ordinary arrays, but they're also kind of cache local amortized complexities as well, and they do support random access, which is tied to the bracket operator. So it is, oh, okay, the instructors got that one. Thank you guys. But lists, on the other hand, are very spread out in memory. So what I mean by that is that if you allocate nodes, all of them are going to be at completely different locations in memory. Even though you have essentially a structure where you have pointers to each of those elements, all of them are going to be allocated at completely different memory addresses, which means that you're not going to have random access unlike the array data structures that you typically use. But a good thing about list is that inserting and erasing from a list, if you're given an iterator, should be constant time, since when you're using a list, you don't really need any sort of operations that require you to index into a specific node element. It's not possible since all of the nodes are allocated different memory addresses. Yeah, let me check the chat again. Could anyone recommend me a resource lab to view iterators? Yeah, you want to go to the STL lecture. Thank you, Ethan. The usual average for the midterm, it varies per semester. So I wouldn't worry too much about that. Yeah, I'm pretty much done with this slide. And to go over some general algorithms in the standard library, you have sort, which takes in a iterator range, which we will talk about a little bit more in a moment. Thank you, Albus, for linking that C++ website. That's really helpful for iterator review. So sort takes in iterators and it will simply like sort wherever you're given. Upper bound and lower bound are interesting functions because they can return you the first element that is either greater or less than a value that you're given within an iterator range. A soft requirement for using these, I believe, is that the range you give it with the iterators needs to be sorted. Otherwise, there's other ones like nth element. I'm not sure if that'll be useful for you guys, but it's something you can look into. And then you also have some heap functions as well, which will take a range and it'll basically convert it into a heap data structure for you. So using those iterators now, you can either push to that you can either push to it or you can pop from it. And I'm pretty sure there should be some access functions for that as well. But I'll leave that up to you guys to look that up. And there's also a few others like remove, bind, copy. All of them really make like writing exam algorithms a lot easier. But I will say that in terms of this, you mainly want to make sure that you know the algorithms that you used in your projects. And I think you'll be ready for the exam that way. And this slide here is talking about the complexities for each of these algorithms. So sort, for instance, requires a random iterator, which means that random iterator is just a iterator that allows for you to start anywhere in your container and go to the end. It's kind of analogous to like random indexing, but with just iterators. A for iterator, it always starts at the beginning of a list and it will continue until the end of it. And in terms of the complexities, I'll leave it up to you guys to review these, but sort is n log n as usual. And yeah, these are pretty straightforward. I think you can add these to your cheat sheet if you want it. And to talk more about iterators, you can kind of think of them as an abstraction to a pointer. So like pointers, you can dereference them, you can increment them, and you can do all of those different algorithm operations that we covered in the previous slides. And the cool thing about them is that these iterators are usually available in the typical data structures that you've been using so far, like vectors and strings and other STL data structures. So they're really useful. And they provide a generally common interface for across all STL algorithms in general. So in this example here, we're declaring a vector doubles and a list event. And all I would need to do is essentially call my function, whatever that is, and then I can specify the iterators that I need to sort this vector. So they're pretty straightforward to use. And similarly, you can use the list that way with the remove function. They're pretty straightforward once you get the hang of them. And Rashil posted a clarification. Okay, cool. And to talk more about iterators in regards to where they are in these containers, they're going to generally be supported by every STL container you can think of. In general, just about all of the ones that you've been using in your projects. So begin is inclusive, which means that it will include the very first element that it points to. But end, however, is exclusive because it points one past the end of the last valid element you have. And you also have some other variants like constant iterators, which restricts you from modifying the underlying data that it points to. And there's a really interesting one called a reverse iterator that actually it starts backwards. So like our begin will actually start at the last element of the list. And if you increment it, it just goes backwards until it gets to the first element. So they're pretty cool. And our begin, as you might think, is inclusive and our end is exclusive. What that means is that our end will actually point one before the first valid element. So yeah, and then there's also a note about how iterator type names are generally really long. So if you want to declare one, you can simply use the auto keyword instead, and that'll take care of it for you. And to kind of touch on the different types of iterators there are and what they do. Yeah, yeah, auto's awesome. It's an awesome thing to have in the C++. That's a big advantage to it. Different kinds of iterators provide different capabilities for you. They're not per se types, but they're rather requirements as to what the iterator can do. So what does auto do again? So auto just, what I think it does is it just infers whatever type, whatever the type of the thing you assign to it is. So if you have auto some variable and you say equal, then I think it can just infer whatever the type is of whatever you're assigning that variable to. If that's not clear, I would highly recommend just looking it up on c++.com because that's a really, it should have a really useful explanation of it. Yeah, kind of, exactly. You don't have to specify the explicit type. So like with iterators, if you use auto, you wouldn't have to specify that really long like iterator name for it. To kind of talk over these briefly, just for the sake of time, the input iterator can read values while moving forward. So that means that you can only read the values that you have and you can't modify them at all. When you compare that to a forward iterator, that can read or write values, which means you can either read the values that you're looking for, you can directly modify whatever it's pointing to. And random iterators are kind of a more powerful sort of version when compared to all of these that allow for you to fully utilize pointer-like arithmetic and comparisons. So just as a quick question, don't worry if you don't know the answer to this. What operation have you seen that is supported by pointers, but never by iterators? Can you guys think of what that is? So some of these iterators do support plus plus and minus minus, namely the random iterator, I believe. For the sake of time, we can reveal the answer. It's actually the delete keyword. So when you're deallocating memory, you usually would use the delete keyword to do that. But there is no support for this for iterators. So that was just a quick trivia. Don't worry too much if you didn't know that. Yeah. And that's all I have to say. Do you guys have any further questions about iterators or the STL in general? So what is the difference between an iterator and a pointer? That's a great question, and I would like to think is more like they're kind of similar in that the arithmetic that you can do to them are somewhat identical. Like you can increment pointers, for instance, and iterators. You can decrement pointers and iterators. But I would highly recommend, it looks like Vashil gave a good answer to that. So I would recommend just looking back in the chat for his message. On the FRQ, would we really have to worry about the type of iterators because we'd get passed in as parameters for appropriate iterators? Yeah, generally, if you've seen the practice of sound problems, if it involves iterators, it'll usually be given to you as input. So yes, I agree with that.
Nigel, just one thing I wanted to
Yeah.
Pop in with. So question 25 is all about iterators.
Yeah,
So when they say like, okay, you are given a forward iterators or whatever, you do have to be very careful to only use that type of like those supported operations, because we will take off points if you use an operation that's not supported by a forward iterator. So just wanted to point that out.
Yeah, exactly. Thank you, Vashil, for pointing that out.
I have a quick questions.
Sure, sure.
So okay, so on the exam, like, do you have to specify like what kind of iterator like you want, or like I can just use like auto for examples?
In general, you don't. I think with the exam problems, the way they're set up now, you don't really need to worry about the specific type of them for the problems you're given. Like for 25, that's all about iterators, so you really can only use the input that you're given. And for 26, it generally doesn't require you to explicitly declare the type of iterator you want. Usually, if you need to work with it, you can just use the auto keyword for that. For question, okay, this is, yeah, we'll specify what the type of them are. Okay, I'll answer one more question and then I'll call it. So if I have a container with 1, 2, 3, 2, 4, 3, and I want it to be 1, 2, 3, how would I delete the 4? That really depends on the type of container you have. So if it's like a vector, you would have to, since it's an array, I'm assuming you would have to rearrange the elements in that container in order to delete it. But that kind of depends on what kind of container you have. For the sake of time, we can move on to the next person that needs to present. Thank you, guys.
Okay, so we are gonna go over sorting algorithms next. Okay. Crystal, am I controlling your screen? are you changing the slides?
Yeah, you're controlling it.
Okay, cool. Oh. Okay. So for sorting algorithms, so I'll try and keep an eye on the chat while I'm talking, but yeah, so we should be familiar with all the elementary sorts, which include bubble sort, selection sort, and insertion sort, as well as the advanced sorts that include merge sort, quick sort, heap sort, and counting or bucket sort. I can just share my screen if it's easier.
Okay, yeah, I can't tell what's going on my screen.
Yeah.
Okay, I'll just stop sharing.
Okay, so these are all the sorting algorithms that you should be familiar with. Yeah, counting sort is considered an advanced sort. It's kind of like a special case because it can't really be used in all cases. Like we can only use that when we have like enumerated types within our container. So yeah. Yeah, counting sort is big O of n, and all the elementary sorts are big O of n squared. So the first one we're going to talk about is bubble sort. So the way bubble sort works is you step through the list, and then you compare each pair of adjacent items, and you swap if they're in the wrong order, and then you do n passes over this. So you start, like on your first pass, you'll start with the first element. On the second one, you'll start with the second element, and so on. And this allows like the largest element to kind of bubble up to the top on each pass. So here's some pseudocode for this. So we can see we have nested loops. And so we pass over it. We do n passes within each loop, swapping adjacent elements that are out of order. So let's take a look at what this would look like. So we compare adjacent elements, they're out of order, so we swap them. And then those are in order, out of order, so we swap. And then as this keeps going, we see that 76 is the largest in the container, and it bubbles to the top. And so then on the next pass, we only go up to 42. And yeah. Yeah, so then we would continue this process, and then the second largest element would bubble to the top, and so on. So this is O of n squared in best, worst, and average cases. But it's done in place, so there's no additional memory needed. And this is a stable sort. So there is an adaptive version that would make this run more efficiently. That is to include a Boolean flag that checks to see if on a pass you make any swaps. So if you make no swaps on a pass, then you know that it's already sorted, so then you can just stop. So on nearly sorted lists, that makes this a lot more efficient. So a stable sort is when you have two elements with the same value. If a sort is stable, then they will stay in the same order that they originally appeared in. And then if it's unstable, then they won't necessarily appear in that same order. There is not O of n extra memory. This was O of 1 extra, so that's just in place. Yeah, and nearly sorted means like it's kind of arbitrary, but there's just like a few elements that are out of place. So yeah, that's a good example in the chat of a nearly sorted list. So like in that list, then if we did one pass on that, after that it would be sorted. So the next time we pass through it, our Boolean would show us that we didn't make any swaps. So that would, then we would be able to stop after that, versus in the non-adaptive, then we would keep going over and over and not make any swaps, even though it was already sorted and we like wouldn't need to make all those passes. So the best case of bubble sort, yeah, so this is what we're talking about. The adaptive sort is where you have this Boolean flag. Oh, sorry. Yeah, so we have this Boolean flag that tells us whether we made a swap on a pass, and if we didn't, then we just break out of the loop. So if nothing is swapped, that means every element is in order. So if we see that every adjacent element, so if we see that every adjacent element is in the correct order, then we know that the whole list is in the correct order. Yeah. So adaptive and non-adaptive, yeah, that's just the addition of the Boolean. That just makes it run more efficiently when we have a already sorted or nearly sorted list. Yeah. So our best case changes when we use the adaptive version, because if the list is already sorted, then it'll just make one pass, see that there are no swaps that need to be made, and break. So that makes it O of n. So yeah, adaptive means, this is correct in the chat, if the list is sorted or nearly sorted, that it will perform better. So next is selection sort. Before I move on, any other questions about bubble sort? Okay. So the way selection sort works is we divide the input list into a sublist of sorted and unsorted items, and then you find the smallest element in the unsorted sublist, and you exchange it with the start of the unsorted list, and then you move the sublist boundaries over. So the way this is worded can be a little bit confusing. The idea is just that you're doing this all in place. You just know that you have like some index in your list where everything before that is in the correct order and is sorted, and everything after that is unsorted. So you just find the smallest element, swap with the first position, and then you find the second smallest element, swap it with the second position, and so on. Yeah, so there's minimal copying, so this is good when you don't have a lot of auxiliary memory. So here is some pseudocode for that. So we go through from 0 to n, and then we find the smallest element, we search for the smallest element starting at I, which is like the index where we start our unsorted sublist. So then you find the smallest element, you swap it with the element at index I, and then you move to the next index. You have like a shorter unsorted sublist. So let's take a look at what that looks like. So we pass over, we look for the minimum value, find that it is 14. So then we swap 14 with the element in the first position. And then now we repeat this with the unsorted sublist, which is now everything except 14. So we'd find 29, and 29 and 38 would be swapped, and so on until it's in the correct order. So again, this is best case of n squared, average case of n squared, worst case of n squared. And this is also done in place, so there's no auxiliary memory. And this is not stable, because I guess it just depends on how you are selecting your minimum. It may or may not keep like two elements with the same value in order. So there is no, there's not an adaptive version of selection sort. So which sorts are stable? I would advise you to look at the Lab 5 slides. There's a slide on this that like puts like everything that's in this slide, but for every sort into kind of one slide, and it outlines the runtime complexity and stability of all the sorts. So O(1) extra, that just means you aren't going to like have to copy anything over, I guess. Like you don't need, like the only additional space you need would be like keeping track of like the index of the start of your unsorted sublist, or like a pointer to an element in the array. And you're not storing like all of the elements in the array somewhere else, if that makes sense. So that's selection sort. Any more questions on that? Okay, we'll move on to insertion sort then. So insertion sort, we also have this division into sorted and unsorted sublist, but it works a little bit differently. So you look at the first element in your unsorted sublist, and then you swap it with every element adjacent to it in the sorted sublist until it's in the proper place within the sorted sublist. So this is what it's going to look like. So if we have, this is after a couple passes, but we have our sorted sublist here on the left, and then we're going to look at 29. We swap it with 76, and then we check it against 53, swap it with 53, check it against 38, swap it with 38, and then 29 is in the correct position in relation to all the elements that were before it in the list. And then we would move on and do the same with 61. So we would just swap it with 76. And then this would end up in the correct order. How does selection sort have an unsorted and sorted sublist? Yeah, so the way it works is when you're finding the smallest element and swapping it with the first, you end up having all of your swapped elements at the beginning of the list. And so after like 3 passes, your first 3 elements will be the 3 smallest elements in that array in the correct order. So that would be your sorted sublist. Does that make sense? Okay. So that's the non-adaptive version. It's O of n squared in all cases. Again, also an in-place sort, and insertion sort is stable. So here's some pseudocode for it. We see that we pass over the whole list. We look at whatever element we're on, and then we swap it with everything before it until it's in the correct place. So this is the adaptive version. So instead of swapping, we move the elements over and insert them into the correct position. So we just move all of those over and put 29 there. So best case for this then is big O of n. And this is a really good sort for small input sizes and for nearly sorted arrays. So let's talk about stability a little bit. So we have this list. We talked about this a little bit, but we have 3 different elements with the same value. And so we can think about this as being like key value pairs, where the key is actually the number and the value is its position in the array. So we want to know if when we sort them, they stay in the same order. So we can see in these examples, in the first one, it is stable because we have 1, 2, 3. And then the second two, the 3s don't stay in the same order. And so those are unstable. So we're gonna go over quicksort now. Quicksort can be a little tough to get the hang of, so it can help to work through some examples with this. Would we be asked to code a sort? No, you're not gonna be asked to code a sort. You're just gonna have to understand how they work and their complexities and be able to answer multiple choice questions on them. The answer to the previous slide's question. Oh yeah, so which algorithms could we use? So we went over this. We said that insertion sort and bubble sort were stable, and selection sort was unstable. So if we want a stable sort, then we would select one of those two. No, adaptive insertion sort does not use a Boolean. We just like, instead of swapping every element, we move them all over and then insert 29 into the correct position. Merge. So merge sort is stable depending on whether or not your merge function is stable, because we abstract away the merge function a lot of the time. We can't say for sure whether or not, but if we have a stable merge, then merge sort is stable. What are these questions? I think you can assume that it's stable, because I think we went over in lecture how merge works, or like an example of how it would work. So we can kind of go with that implementation. And yeah, someone asked about the practice question where you have to merge intervals. Yeah, so I would look back at the lectures for that. They went over how merge would work. Don't have a ton of time right now, so I'm gonna keep moving forward. But yeah, you can find that in the lecture slides, and I think that would help you. So, okay, quicksort. So the way quicksort works is you pick a pivot from the list, and then you swap elements in the list so that everything less than the pivot is before the pivot in the list, and everything greater than or equal to the pivot is after it in the list. So after partitioning and swapping elements so that this is true, then the pivot is in its final position within the sorted list. So then we recursively sort the sublist of the smaller elements and the sublist of the greater elements. So we partition the array by putting element where it would go if the array were sorted. So bubble sort, yes, bubble sort is good for nearly sorted. Well, adaptive bubble sort is good for nearly sorted. Non-adaptive bubble sort is not good for nearly sorted. Yeah, we're gonna go over quicksort a little bit more. So here we choose 42 as the pivot. So we look at these two elements, one at the first and one at the last before the pivot. And so we increment the left pointer until we find an element that is greater than the pivot. And then we decrement the right pivot, the right pointer until we find an element that is less than the pivot, and then we swap the two. So we see that 14 is less than the pivot, and 53 is greater than. So we can swap these. And then 38 is less than, 76 is greater than the pivot, and then 53 is greater than the pivot, 61 is greater than the pivot, 29 is less than. We swap them, and then once the left and right pointers are equal, then we swap that with the pivot, and the pivot is in its correct spot where everything to the left of it is less than and everything to the right of it is greater than. So yeah, so then we run quick sort on each of the sublists. So let's think about the complexity a little. Well, first, do you guys have any questions about how exactly that works? To get an idea of what kind of questions could be asked, I would look at the Lab 5 questions and any questions that are in the practice multiple choice. We're not going to have to code them for the FRQ, I'm pretty sure. Can someone confirm that? The pivots for sublists are not always going to be the rightmost element. In this example, that's what we're doing, but how you choose your pivot depends on your implementation. Okay. Quicksort can definitely be a tough one, so it can help to work with some examples. But we're going to talk about the complexity a little bit. So if we select a pivot that always divides the list in half, then we this is what that's going to look like. And so we partition log of n times, and then we end up with O of n log n, which is best case. So, but if we select the largest or smallest element, then this is what our partition ends up looking like. And so we have to partition n times, and so we end up with a complexity of O of n squared. Okay, so then we see that we have a best case of O of n log n when we choose a pivot that's right in the middle, and a worst case of O of n squared. But the average case ends up being O of n log n because typically we end up choosing something that is toward the middle, versus it's a lot easier to choose something that's toward the middle than to choose one of two of the most extreme elements. So the memory consumption for this is we have log n auxiliary memory, and quicksort is not stable. So if we could find the median in O of n time, we would be able to choose the median as the pivot every time. And so our complexity would be big O of n plus big O of n log n, which makes it n log n. So that would improve our worst case because we would be able to choose the median every time. And then if you could find the median in O of 1 time, it would still be O of n log n because we would still have n iterations over the list as we swap the elements, and then we would have to partition log n times, so that is still big O of n log n. Okay.
All right. I think I'm just gonna switch to my computer just because I would like to draw if I have to. So, yeah. Can you stop screen sharing so I can share?
Yeah.
All right. Cool. Okay. So for me, we're just gonna talk about priority queues and heaps. So yeah, let's go. Okay. So a priority queue. A priority queue is an abstract container type that supports two operations. It supports insertion and removal of the item with the largest key. And so here, largest really means most extreme, because say we have a priority queue of integers. Depending on the functor you pass in, it might be the largest element or it could be the smallest element. So largest key really should be Oh, she's back. Okay, or I don't know. Anyway, so Heapify, the way Heapify is implemented is you call fix down from the bottom up. And the reason that it's O of n is because it saves time on the leaf nodes. Because when you call fix down on a leaf node, it doesn't have to go anywhere because it's already in the right place. So that's about half of the nodes in every tree. So that's how it saves that time. So when you use the STL's range-based constructor, it calls Heapify. That is one reason that you shouldn't, if you've got a bunch of elements, you shouldn't just insert one at a time. It's always best to use the range-based constructor if you can. And also, the standard make heap does the same thing as Heapify. Okay, so this is just a little thing that shows why fix up is less efficient than fix down, because yeah, you have to go to a depth of log n and do this on n over 2. Wait, hold on. Let me think about it. Right. Okay, here you go. This is what it's showing. So it ends up being O of n log n when you do a, what is it, top-down fix-up, I think? It's bottom-up fix-down. I think it's a top-down fix-up. Yeah, top-down fix-up is worse because it ends up being O of n log n because they have to do it on every element in the tree, and it doesn't save much. The only place it saves time is on the root node, which is not enough. And just talking about how bottom-up fix down. And so there's like a little bit of math here. I guess you can look at it on the slides if you want to, but I'm not going to really go over it. The main thing to think of, the main reasoning to think about is that fix down on these and these nodes does nothing. So it saves time. Okay, so here's just more going over the array representation of a binary heap. So we index like this. So we start here with 0, and then 1, 2, so on and so on. And then that's how we say that this is the array representation of a heap. And then here's the indices once again. So right now the array is messed up. So we want to make the heap out of the array. And so we've already said that we want to do bottom up fix down. Okay, so all of these, there's nothing to do because there's nothing to fix down because it's at the bottom. But then we start our first round of fix downs. So we start with, yeah, this one right here. And so it's the same as the one as its child. So there's nothing to do. So it also has no work. This one, I don't remember. Yeah, okay. Yeah, so this one also has nothing to do because it's greater than all of its children. So 8 also stays in the same place. Then we go to 4. 4 needs to be swapped with its greater child. So that's what's happening here. We swap 4 with 7. And so 7 becomes the parent after that. Then we have to do the same with 5. So 5 needs to be swapped with its greater child. So we swap down. Okay. Yep, swap down. 8 becomes the parent, 5 becomes the child. But then we need to keep going downwards because it's possible that it still has greater children. So then we look at 5 and 6 and see that 5 is smaller than 6. So we need to swap 5 with 6. And then we have 6 there. And then, of course, the same thing was happening in the array representation the entire time, but it's probably easier just to look at the tree when you're thinking about it. And then finally, we go to the root. And so this is our final round of fix downs. And because it's 2, it needs to be swapped with its greater child. And so that was 8. So swap down, and it's getting a little repetitive now, so we just keep doing it. Swap 2 with 8, then swap 2 with 6, and then with 5. Okay, and now it's in its right place. And this is the final heap. So now insertion, this is just like some animations showing how insertion works. We add the element that we want to add onto the end of our vector, which will also add it onto the end of our PQ, or sorry, our end of our tree. And then we fix up from that location. So here is where that element is added, it's 6. And then we see that it is greater than its parent, so it's going to be swapped up there. And then it will be still greater than its parent, so it's going to be swapped up there. So we can just follow that here. Okay, yeah, and it ends up here. All right, and yeah, and the reason it doesn't go up here is because 8 is larger. Good. Okay, so then pop is just, it's pretty similar. Instead of using fix up, we're going to be using fix down. And so what you do with pop is you take the root node and swap it with the final node. So it's the same as taking the first element in the vector and swapping it with the last element in the vector. And then you delete that root. So since it's a vector, all you'd have to do is pop back. So you would just shorten the vector like that. And then you fix down from the root. So here's that. Okay, we swap them. And then we've popped back. So see there's our 8 here, and then it's gone here. And then we're going to fix down. We've gone over fix down a couple times, but it's got to decide which one it's got to go down. Goes down. Yep. Okay. And then it ends up in its right position. Okay. I don't know. What's the difference between these two slides? Okay, whatever. So push and pop, because they only require a single swap and then a fix down or fix up, are both log n. And then top just returns the most extreme element, so that's O of 1. So then we have to talk about heap sort. So there's a pretty big difference between heap sort and Heapify, actually. So Heapify turns an unsorted array into a heap, but heap sort takes a heap and sorts the data from it. Or it doesn't actually have to be a heap. It takes an unsorted amount of, it takes an unsorted array, makes a heap out of it, and then uses that heap to sort it, basically. So here's how it works, I guess. So you heapify the array, constructing a max heap. Then you take the top element and swap it with the last element on the heap. And then you leave that element there and pretend that that's no longer part of the heap, and then call Heapify on the rest of the array again. So you've already gotten the max element, you put it at the end, and then just call Heapify again. Or sorry, it's not called Heapify, it's you call fix down, actually, sorry. But it basically makes the rest of it into a valid heap, is the idea. Yep, okay. So we start with 8, and we swap it with 3. So now we treat that as if it's no longer part of the heap, that 8. I don't know when we're going to get there. Oh, right. Okay. Yeah. So that's what this is showing. It's saying that this is our heap now. And so then we fix down 3. So it started here, then it goes down here, and then it'll go down here. So it'll be right. So then we've isolated the largest element there as not part of the heap anymore. And then we just have the rest of this, which is still a valid heap once we've called fix down. And then we'll do the same thing. We're going to swap 7 with 1 and then isolate that and then call fix down again to make another valid heap. And so what that will end up doing is by the end, you'll have a sorted array. Okay, so someone asks again, what's the difference between heap sort and Heapify or make heap? So heap sort is an algorithm which sorts the array. Heapify or make heap is an algorithm which converts an unsorted array into a heap. So a heap is not necessarily a sorted vector or array, right? It's just a heap. I don't know. We've talked about that, right? So you need to use, how do I explain it? In heap sort, you use that heap that you've built to get the maximum element, put it to the end, and then isolate it, and then use those remaining elements to make another heap, and then get the maximum element, and then do that. So then someone asks, this would only work for a max heap. And so you would use a max heap if you'd want to sort in ascending order or smallest to largest. but you would use a min heap if you want to sort in reverse order or largest to smallest. So yes, if you wanted to sort in, I guess you could probably do it with a max heap the other way too, but I don't know exactly. No, I don't know if that would work. I wouldn't try it. I would just say you should use a max heap to sort in ascending order and a min heap to sort in descending order. Okay. I think the rest of this is just heap sort animations. So I guess maybe you can look at that if you want, but I think it's, I don't know, it's just pretty repetitive. So then the things that you need to know for the exam are knowing how to represent a heap as a vector. And so remember, that's just labeling the nodes with an index starting at 0. So the root node is the 0 index, and then left to right would be 1, 2, and then left to right with the next level is 3, 4, 5, 6, and then so on. You should also know how Heapify and Heapsort work and what the complexities are. So just review. Heapify is O of n, and Heapsort is O of n log n. Yep. And then you should look at some of the practice problems which insert and remove from a heap. I don't know why there's even more Heapsort animations here, but I think, yeah, that was the rest of the slides. Is Heapsort stable? I don't think so. No, I don't think it's stable. Does anyone know? Does anyone know for sure? I'm pretty sure it's not stable, but yeah. Okay. Yeah, people are saying no, so. Yeah. Any other questions on heaps and Heapsort and Heapify? I kind of went over that quickly, but I don't know. Most of it was just animations. Okay. Heapsort is impossible with linked lists. I think to do it in n log n, it would be impossible with a linked list because using a heap requires indexing to speed up, like to have like an optimal time complexity. You can't index with a linked list. So I would say Heapsort is impossible to do in n log n with a linked list, at least. Is it relevant to think about best and worst cases for Heapify?
Sorry, time complexities.
Right. I guess if it was already a heap, it might be O of n. No, it is already O of n. So Heapify is going to be O of n even if it is already even if it's already a heap, because you have to check every node anyway. I think that, right? Yeah, I think so. So I think best case at least, and then worst case means every element needs to be fixed down the maximum amount, which is still O of n. So I would say it's probably still O of n either in best, worst, and average case for Heapify. Someone asks, a heap is not sorted. So that's a question I think that doesn't really make sense, because a heap is kind of an interpretation of an array. So you could ask, is the underlying array of a heap sorted? And no, the answer is no. And yeah, it's not ordered either, because you can't insert any element into it wherever you want.
I have a question about the Heapify and the Heapsort again.
Yeah.
They're confused. So Heapify is taking something that's unordered array to make it to like a max heap or min heap, right?
Yes.
And Heapsort, it has to be a ordered heap already, right?
So Heapsort, you call Heapify on the entire array first. That would make it a heap. Then you swap the element, the most extreme element with the last, and then you make the remaining elements a heap again. So no, you can also call it on an totally random array as well.
Okay, so Heapsort, you can call it on like any heap.
Yeah.
Okay, got it. Thank you.
Yeah. Any other questions? Is Heapsort in place? Yeah. Heapsort is in place. You can definitely, I think it'd be pretty weird to, well, no, you could totally implement it not in place if you wanted to, but yeah, it works fine in place. Yeah, this is the last topic. Is Heapsort
Wait.
adaptive? I don't think that we have an adaptive version of Heapsort, really.
One more question. So let's say if like the exam give me like an unordered array or vector, and then ask me what's the best way to sort that. I mean, I'm just talking about Heapsort and Heapify. Which one would be the best?
Oh wait, so someone asked you to sort it, and
Yep.
well, Heapify wouldn't sort it, so you'd have to use Heapsort, right?
Okay, so I'm confused about what's Heapify again right now. Then.
So Heapify turns an array into a heap. Now remember, heap is not sorted. Heap just means that it follows the heap ordering invariant, which means that the most extreme element is at the beginning, and then its children nodes will always be smaller or less extreme than it.
Okay, got it. Thank you.
Yep. Yeah. Should we end the recording then? I don't know. Yeah, I think we should. Chris looking at it.